Okay, let's go ahead and get started. My name is Paul Hernday, and I'm an applications engineer with Solmetric. We're located in Northern California, just about an hour north of San Francisco in the wine country. And today's webinar is about using the IV curve tracer in array commissioning and maintenance. And this is a little bit different than our usual webinars. And we're going to focus for the first half of the hour on more of the business aspect of why it's important to adopt curve tracing for these types of applications. And in the second half, I'm going to explore the use of our new poster, which is a PV performance troubleshooting flowchart. And I'll go into that in detail. The format is presentation with stopping for questions from time to time. So I will look in the questions field to see if you have any. And I will try to answer any that as many as I can. And if I don't answer your question, please drop me an email, and I will definitely respond to it. And I may have to go off and research something too, depending upon how tough the questions are. I see we have attendees from all over the world today, so that's great to see, even from France, which is awesome. That's one of our more distant participants today. So before we get started on the content, I want to just briefly update you on what the product is, or refresh what the product is. So we're going to be talking about the PV analyzer, which you see in the upper right-hand side. And there are two parts to it, two instruments. One is the curve tracer, which is in the soft case. The other is the Sol sensor, which is a wireless reference sensor that has an irradiance sensor at the tip of it, up at the top, and some sockets at the back end, at the bottom for connecting thermocouples, which are attached to the bottom of your module under test. It's fully integrated, has its transmitters and rechargeable batteries inside, and it connects conveniently. It clamps very conveniently to the side of your module, to the side of the module frame. So it's guaranteed to be aligned in the plane of the array. And these talk to each other wirelessly and to your PC, which is the command center for your measurement. Most people these days are using tablets for this because our software is optimized for touchscreen, and it makes it really, really fast in the field. By far the fastest curve tracer out there as far as just production gathering data. This unit goes to 1,000 volts and 20 amps and has approximately 0.5% accuracy for both current and voltage. This is the wireless network. You see the Sol sensor mounted on a module up at the upper left. And it's a mesh network, so the wireless will communicate in any path necessary. If you're really far from Sol sensor, then the high power transmitter in the PV analyzer itself can act as a relay station. There are 3 dots that are published on the screen to which the measured curve trace is compared. Those 3 dots are generated from an internal PV model, which is informed by all of these factors that are listed in the parenthesis up at the top. And so it's really nice. You have an actual set of reference dots at the temperature and the radiance at which you're measuring to compare the trace. You don't have to translate the trace down to STC conditions and lose some of the physical insight. I'll skip that one because I've kind of explained that already. So in the first half hour, I'm going to talk about the drivers for adopting curve tracing, and specifically the Solmetric curve tracer, because it has some very distinct advantages. And if I forget to mention them, please ask me. I get so enthusiastic about curve tracing in general. And then in the second half hour, I'm going to go through the troubleshooting flowchart. So this is my set of topics that I'm going to talk about in the first half hour. The benefits of IV curve tracing for performance testing of PV circuits. And quickly to summarize it, it's the most complete measurement compared to any other measurement available, such as independent measurements of voltages and currents. It gives us the best troubleshooting clues. It's the fastest in terms of gathering your data, and it's also the safest. So I'll touch on each one of those in a little bit of detail. First of all, most complete. So by way of review, this is your normal looking IV curve for a module or a string. And these terms around the edge of the graph are going to be used throughout this webinar. So I'll just mention there's short circuit current, max power current at the upper left, and at the lower right, max power voltage and open circuit voltage. And then in this drawing, you see the 3 dots that I mentioned earlier. And so we can think of this in 2 ways. We can either say that this represents the measured curve that happens to land right on the model, the predicted values, or we could just say these are markers that represent those places on that curve. So for the time being, I'm going to say that these simply mark those places on the measured curve, and later I'm going to introduce the concept of performance factor. So you'll notice that in this drawing, the maximum power point defines a rectangle with the dashed lines that has the dimensions of height, max power current, and width, max power voltage. And so that defines an area shown in green here, and that area has the units of watts. It's a power value because we're multiplying current times voltage. Now, the max power point is always at the knee of the curve, and if you slide the operating point to the left, you get a slightly taller rectangle, but it's much narrower. And so the area is less than the Pmax that we saw in the previous slide. Similarly, if you slide the operating point to the right to a higher voltage, you get a little bit higher voltage, but you get way less current. So again, the area is less than Pmax. And this is the kind of thinking that the inverter goes through when it tries to find the max power point. It slides the max power point around and figures out that, oh, yeah, that's right at the knee is the maximum power point, and then it stays there. But it keeps checking every little while to see if that's still the best place. Now, the next topic to introduce is the concept of the fullness of the IV curve, because it's one thing to be operating at the knee of the curve at the max power point, but the next question is how max is that power for a given ISC and VOC value? And in this next slide, we kind of see that effect. I've drawn here 3 different IV curves with a different roundedness of their knee, or different fullness of the IV curve, as I like to say. So you can imagine if this IV curve were really full, that it would be square, or rectangular. The trace would come across, the red line would come across from ISC, and there'd be very little, if any, curvature at the knee. Let's say 0 curvature, and it would come right out to VOC, and it would drop straight down. But of course, we can't build PV modules like that, so we always have some of this radius in the knee of the curve. But the more full it is, the further we are up to the corner, the more power we're able to produce for a given value of ISC and VOC. And that fullness is expressed in a parameter called the fill factor, which is definitely the most underutilized and wonderful PV performance parameter that we have for troubleshooting purposes, and also for feedback to module makers on warranty claims. It expresses the fullness of the curve, and it does that by forming the ratio, or dividing 2 different rectangular areas. It takes the area defined by the green rectangle, defined by the max power point measured, divided by the area of the blue rectangle, which is defined by ISC and VOC. And when you divide those 2, you get the fill factor, which is shown in the green, within that green rectangle. And that's 0.7 to 0.9 for poly and monocrystalline. I'm sorry, I should have said 0.8. And 0.65 to 0.75 for most thin film technologies. And why is it important? It's shown in this formula up towards the top above the graph. So the max power is that a string will deliver is equal to the fill factor times ISC times VOC. We're just taking the formula that's in the green area and saying IMP times VMP is max power, right? So we're taking that and putting it on the left side of the equal sign up above. and we're then taking ISC and VOC, multiplying both sides by that. So up at the top we get fill factor times ISC times VOC. So for a given ISC and VOC, the fill factor determines how much maximum power you can get. And that's really beautiful because anything that distorts the IV curve, like a change in slope anywhere or some notches caused by shading or soiling or shorted bypass diodes or something like that, or partly conducting, will show up as a distorted curve, leading to a lower fill factor, leading to lower maximum power. The next concept to get before we go on is the performance factor, and the performance factor is a measure of how close we're coming to the predicted max power. So if our predicted curve is the dashed red curve, and you see how there are predicted values of ISC, max power, and open circuit voltage. If our actual measured curve is the solid red one, you can see we're a little low on short. Oops, I should have gotten rid of. Darn it! I should have gotten rid of this IMP and VMP labels on the axes. So please ignore them. So you can see the measured curve is a little bit low in short circuit current, a little bit low in open circuit voltage, and as a result, it's low in the maximum power as well. And if we divide the measured maximum power, in the gray, which is the gray dot, located at the gray dot, I should say, by the predicted max power, which is located at the red dot, and multiply that by 100 to convert it to a percentage, we get the performance factor. And that is the primary metric that we use in the PV analyzer to express whether it's a good string or a bad string, or whether there are problems in it. And the fill factor that I mentioned earlier is a very helpful troubleshooting tool as well. So that is all preparation for this, which is leading into a discussion of the completeness of this measurement. So let's say that the solid red curve represents the expected natural good performance of a particular module that's loaded into your model in the PV analyzer. So what we expect is that the IV curve will pass through these 3 red dots, marking those cardinal points in the model. So this one does, and so that's the ideal normal curve. But in actual practice, we often see curves that deviate from the expected in 6 different ways, and sometimes in combinations of those ways. So number 1 is steps in the IV curve. It's often caused by shading. Number 2, the short circuit current is not high enough. Number 3, the open circuit voltage is not high enough. Number 4, there is too much curvature in the IV curve at the knee. Number 5, there is too little slope in the vertical leg of the curve. I should point out that in the case of curve number 5, the curve doesn't really stop there. I just simply stopped it there to avoid confusion with too many traces. The rest of the curve, if you continue curve 5 upwards and to the left, it would be a normal curve. It would just continue and bend over. And the number 6 is a case where we have too much slope in the horizontal leg of the curve, and again, that curve, you can kind of imagine that curve continuing out and then continuing down normally. So all of these 6 deviations reduce Pmax, and therefore they reduce the performance factor. And so if you see a performance factor due to, say, 80%, it could be due to any one or a combination of these deviations. Deviations 1, 4, 5, and 6 reduce the fill factor because they change the shape of the curve. And so fill factor is a nice way to detect whether those sorts of things are happening. So to summarize, it's the most complete method because the IV curve gives you all the dots on the IV curve, in other words, the whole shape, plus ISC, VOC, max power, current, and voltage, the max power, and the performance factor and the fill factor. And another nice thing about it is that the results are independent of the inverter performance and any issues with a shading or array, a shading or soiling elsewhere in the array. And the reason that is because the combiner is taken offline, the fuses are lifted, and the individual strings are measured, isolated from everything else. So you find out what the actual string-specific max power value is. If there's a cloud passing over some of the other parts of the array on that same inverter, you don't care about that. You don't care about the fact that the inverter is being pulled away from its proper max power point by that shading, because you're isolated. So the next really important benefit is that it provides really excellent troubleshooting clues. The IV curve shape suggests possible causes, which we'll discuss later, and the selective shading method reduces troubleshooting time. And I'm going to show you just one slide on that. Selective shading is used to find the bad module in a string of modules without the requirement for actually disconnecting the modules from one another and testing them separately. So the way it works is you use a piece of cardboard or black rubber or something to switch on all the bypass diodes in a module, and you measure the string again. And if the problem module is the one that you put the cardboard over, then you will electrically bypass it and eliminate the problem from the string. So that's the method. If you put the cardboard over a non-problem module, you'll still have the problem in the string IV curve. So a way of looking at that in terms of IV curves themselves is to look at this graph at the bottom. And our very first measurement of the string, which exposes the problem, is the solid red curve. And we see that we have a little step at the bottom, which is typically 10 or 12 volts wide, which means that our max power point is going to be shifted to the left 10 or 12 volts. So we'd like to find out what that is, because that's costing us money. So we measure this string of modules 10 times, which is quite quick, each time putting the cardboard over a different module in the string. And what we're going to see is 9 traces like the dotted red trace that have the step in it yet, and 1 trace like the dotted blue one that does not have the step. And that dotted blue one corresponds to when we shade the bad module. So that's the selective shading method, and we've been telling everybody under the sun about it because it's such a powerful method for troubleshooting down to the module level without so much time and without disconnecting and reconnecting and removing so much hardware. It can really be a nuisance, and it can introduce workmanship errors. The next, I'm going to stop here and see if there are any questions. No questions yet, so I'll just keep going. The next driver for adopting curve tracing is that it's the fastest measurement. And the reason for that is that it's one measurement per string at the combiner box, and there's no need to come back later and clamp meter the strings when the inverter is operating in order to find out what the operating current is. In addition, data analysis is automated by the Solmetric data analysis tool, and it generates a really professional looking report. And a lot of people point out to us that the measurements are fairly easy for them to make. It's the data analysis and reporting that is quite time consuming. And that tends to be a little bit more expensive labor too. So speedier measurements, the speedier is not just the measurements themselves, but the whole process, saving time in the whole process. So a quick tour of that point. Here's the typical setup. This happens to be a parking lot array, but could be any type of array. You put the PV analyzer near the combiner box. You open the DC disconnect. You lift all the fuses, and then you clip the giant alligator clips onto the bus bars, and then you insert 1 fuse at a time in order to make the measurement. Some of you have seen this drawing before. So this is that same thing, just converted to a cartoon. You're pushing in 1 fuse at a time to measure the corresponding string, using the combiner box as basically a single pole multi-throw switch. And you see the measurement on your display, and you press save, and you save it to a tree. And I'll show you that in a few minutes. This is actually the way it works. You press measure now in the upper right-hand corner there, that's step number 1. In about 4 or 5 seconds, the measured trace comes up and slides over to the left. It squinches itself to the left a little bit to make room for the tree. You touch the string that you're measuring with your finger, and you press assign and save, and it will store it at that location in your array. And you can come back and measure that string in coming years, and you'll touch the same string, and it'll save it, and that number following that string will increase according to the number of measurements you've stored there. And every measurement is time and date stamped so that you'll be able to measure in the future the degradation in that particular string. So when you press assign and save, the display stretches out again, and now we see the measured curve, which is in red, compared with the red dots, which represent the expected. You export your data by going to File, Export Traces for entire system, and then you analyze that data with the data analysis tool, and it produces these three types of displays: a string table for all of your string measurements, the main values of the parameters, the statistical summary up at the top, and even some limit checking. If you want to set the allowable limits in blue, it will tell you which strings are not acceptable. In the upper right, you'll get, for each combiner box, you'll get a family of IV curves. And in the lower right, for each parameter, like Pmax as shown here, you'll see a histogram or a frequency distribution plot, which shows you how closely your values are clumped together. So each count on the vertical axis represents one string. So all of that is automated and very fast, and it produces a very professional looking report, which I wanted to show you a copy of. This is the front page, and you can customize this with your logo or your customer's logo. String statistics, string data, compared to predictions, histograms for different parameters. This is what you want to see on fill factor. You want to see a nice bell-shaped curve for fill factor. And then, of course, the IV curves at the combiner box level. Oops. From current slide. There we go. And then this is another thing that saves time and effort. Data management and sharing it between offices and has always been a hassle. Compiling spreadsheets and then mailing those to people. In the case of the PV Analyzer, all you need to do is grab the project file for the particular project that you're working on, which contains all of the data, all of the setup conditions, all of the modeling, all the design parameters of your array. Just attach that to an email and send it to someone. And when they get it, they simply double-click on the icon, and it launches their PV Analyzer software, which looks like this. And they can see, they can go through the same tree that you saved your data to, and they can look at all the data, and they can export it and do a data analysis of their own if they want. So it's very, very powerful concept to wrap all of your data and your setup conditions in a file. It also makes it easy to share your results with our staff. So if you need help from us with tech support or application support, the first thing we'll ask you is to, hey, email us your project file, and then we can see exactly what you did and help better. So the final thing I want to do on the time point, time advantage, is to take a look at comparing with a cycle time analysis, comparing IV curve tracing with measuring open circuit voltage with a digital voltmeter or digital multimeter, and then returning when the array is operating and measuring the operating currents with a clamp meter. And I did this analysis recently, and I'm going to take it to somewhat further as well, but I think this is sufficient at this point, sufficient detail on the left to illustrate the basic concept, which is that largely because you have to visit the box twice, once for VOC and once for operating current, you wind up with spending a lot more time per string overall and per system if you go with those discrete measurements compared to the IV curve measurement, which is done all at one time. And the numbers that came out at the bottom of this analysis were for For a system up at the top, see that I assumed a number of combiner boxes in my spreadsheet of 10 with 12 strings per combiner box. And then I made some other assumptions about the time it takes to do different tasks within the process. For the various assumptions I made, the total hours for the system for IV curve tracing was 2.7 hours. And the total time for doing it with discrete measurements was 2.2 plus 3.2, or 5.4 hours. So roughly a 2-to-1 difference. And I found that if you play with the number of combiner boxes in the system and the size of the system, of course, which is number of strings times number of combiners, the numbers vary somewhat. And they also vary according to how much time it takes you to move to the new combiner box. So I assumed 600 seconds or 10 minutes. So based on your assumptions, you'll get somewhat different numbers from this, but I tried to estimate it as close as I could to what experience shows us. And so this illustrates really clearly a big time savings if you can just do it all at once. And another benefit of curve tracing is that this is a strategic benefit. You can do all of your curve tracing before the inverter is even installed. So if you finish your array early, you can have it completely checked out and have all of your performance testing, all of your basically your startup or commissioning test even for the array can be done while the inverter is being installed. And that guarantees that when you start up your inverter, you're going to have no problems from the array, and it saves you time because you've been able to avoid the problems at that expensive stage of the project. So I'm going to check again for, see, it should jump back into the slideshow. And I'm going to check again for questions. Let's see if we have any questions. No questions at this point. So that leads me to wonder whether you can hear me. Can you still hear me? If so, type something into the question field, please. Okay, good. You had me worried there. Okay, great. Everybody can hear. So I'm going to assume from all of this that you're mainly here for the second half of the hour, which is fine. So we've gone through most complete, best troubleshooting clues, fastest, and now I want to just point out that it's also the safest. And the reason for that is that there's less handling of conductors. A lot of times when you go into a combiner box with a clamp meter to measure on the active system, you have to pull and push on conductors because not enough test loop was left, strain relief loop, and that means you've got both hands in the combiner box, you're spending extra time, and there's more of a chance of doing something that would get you in trouble. And probably more importantly, when you're doing curve tracing, your combiner box is isolated from the inverter and the other subarrays. So you have much less of an arc flash hazard than you do in the case where you're working with a clamp meter inside of a live combiner box that's fully connected to the rest of the system. If you have not read the recent article on flash hazards in SolarPro, I strongly encourage you to do so. There's another strategic opportunity with curve tracing that we're seeing more and more of opportunity for in large systems, which is that if you have monitoring at the zone level at your inverter, as shown on the upper left-hand side here, these little red symbols represent current monitors attached to each of the combiner box inputs or outputs, I should say, at the inverter, coming into the inverter. So your monitoring system will tell you how much current you have in each subarray. And it's really nice to complement that kind of zone level monitoring, that granularity, with IV curve tracing at the combiner box level, because it's so fast You can blow through a combiner box in very, very little time. And there are a couple of reasons for taking this approach. One is if your zone monitor tells you that a particular subarray is a little bit low, you can go out there with your curve tracer and measure those strings and know exactly which strings are causing that issue and chase it down to what the issue is. It gives you a better understanding of what's bothering your array. And it gives you a better understanding also of how sensitive your current sensors are. In other words, are they set at the right level to detect the kind of problems that you want to detect? So it's a really nice complementary use of curve tracing. And another application in this situation is to just go out with your curve tracers and every month measure a couple percent of your combiner boxes, and take a couple different percent, a different couple percent each month. And that gives you, again, an ongoing understanding of how your array is aging, and it populates your database in the PV Analyzer software so that in the future you'll be able to look through that data and plot trends in performance parameters. Okay, now we're into the second half hour, and I'm going to be talking about using the troubleshooting flowchart. But first I want to frame that a little bit by showing you this slide. At the center of this, the gold lettering represents the actual string performance, which is what we'd love to be able to measure usually, unless you're trying to measure the amount of soiling or something like that. But usually we want to measure the actual native performance of the PV modules. But there are some of these obstructing or clouding issues, which are weather, obstructions like shade and soiling, and then also measurement issues down at the bottom of that chart. So all of these are kind of a smoke screen that can cloud the actual string performance. And one of the benefits of, one of the actual motivations for doing the troubleshooting flowchart was to help our users, whether it's our curve tracer or somebody else's curve tracer, or even people who are using voltage and current measurements. You want to understand what the impacts of each of these three different impairments are, so that you can QA your own measurements and not be sending warranty claims back to a module maker for reasons that are not really substantial, because it's a waste of your time and their time. So again, these are the 6 deviations that I mentioned earlier, and in the flowchart, this is used as a key to the different branches of the tree. So depending upon which of these you see in your IV curve, you'll branch off at a different level in the tree. And you should always check for these other causes before deciding that it's a module degradation situation. So here is the flowchart, and you can request a free flowchart from us. We'll mail it to you by if you go to freesolarposters.com. That's a website of ours for managing posters. It's a 2 by 3 foot wall poster. And what I'm going to do in the next the rest of this half hour is to go through this and show you, starting from the top, how you use it. So I'm going to jump out of this slide and bring up the poster itself, which is shown here in much higher resolution so you can read it. So there's the upper left-hand corner, just for reference. Here is the key to the thing, which is the 6 deviations. And down the center of it is a series of questions you ask yourself as you're troubleshooting or trying to chase down what the issue is. You start up at the top, and the first question is, does the measurement return a useful IV curve? And if you get no curve, if the answer is no, you go to the right and you check to see if you have a completed, if all the connections are proper. If all the connections are proper, you still don't have a useful curve. Well, maybe the issue is that you have some dropouts in your curve. A couple times customers have told me that, and it turns out that what it was that they had an open circuit, or intermittent circuit, I should say, somewhere in their circuit, and so they were getting vertical notches in their IV curve. But assuming you don't have those problems and you get a useful curve, the next question is, what is your performance factor? Are you into the 90% range where we want to be? And again, performance factor is the max power measured divided by the max power predicted times 100%. I guess I left out the 100% in the formula. If you're in the 90s and it has a normal curve shape and it's pretty much in the same performance factor range as all the other strings you've been measuring, then you exit with the yes and you save your data and move on to the next string. Measure the next string. So this would be your production loop if you're doing, say, commissioning or assaying a system or recommissioning it. However, if your performance factor is low or you're not a normal curve shape, then you exit that box with the no and drop down to check if there are steps in the IV curve. And the reason we put that first is that quite often steps in the curve are caused by shading or debris or litter or soiling, and that's something you can do something about. And it tends to mask the performance pretty well. So you want to take care of this first. So if you have steps in the IV curve, you exit that box to the left and you go into this orange area, orange bordered area. And the first question is, do you have shading? Because shading, as shown directly below that, with an example of tree shading, tends to cause a lot of stepping, kind of roller coaster look on the IV curve, which drastically reduces the power, even if it's fairly slight shading. If it affects several modules, it's going to drastically reduce your power. If you don't have shading, then you exit that box with the no and move to the left. And do you have random soiling or debris or snow on the module? And the example that I've given here is seagull soiling. This is from New Jersey, I believe. A lot of these pictures came from customers who are really helpful in sending examples. And you'll see that because of this really intense soiling, the IV curves have lots of little steps in them. These are 10 or 12 volt wide steps which correspond to the turning on of a single bypass diode that is protecting a group of cells. If you don't have these issues, then you go further to the left. Well, maybe you have mismatched modules because some of the modules have been replaced over time with modules that don't have the same short circuit current. Well, if they're all original modules and none of those are issues, then you look for other things like cracked cells within one of the modules, or maybe there's a place where there's a burn mark, or maybe you can't even see the burn mark, but maybe there's a hot spot caused by a high resistance effect that's causing a bypass diode to partially turn on. So that's the way you use this chart. There are times in each of these legs of the IV curve where you get close to concluding that you might have to contact your module maker. And those are these little circular arrow icons. At those points, when you get to those points, you may have to replace your module. So I'm going to check to see if there are any questions at this point. No questions yet, so I'm going to continue on down. So suppose we did not see any steps in the IV curve. Then, of course, we would not go to the left on orange number 1. We would drop straight down and check to see if it has a low short circuit voltage. And the reason I put this next is because a lot of times people will use their irradiance sensors improperly. They won't be facing in the plane of the array. They'll be pointing straight at the sun, or they'll be pointing straight up, lying on the ground or on the roof, and not necessarily in the angle of the array itself. So we'd like to get that problem out of the way early as well. So if you have a low ISC compared to the prediction, that's case number 2 in the deviations, and so you go into the orange block. The first thing you check is to see if you have uniform soiling on the array, because that is just like not having enough light. If you are nice and clean, at least you don't have the broad film, uniform film of dirt, then you say no to that box and you go to the right and check to see if you have dirt dams or strip shade. And these are abbreviations because of space, but what that means is either you possibly have a collection of dirt at the bottom edge of the module, or there's a strip of shade at the bottom edge of the modules cast by another row of modules, or cast by a parapet wall, or a railing or something like that. That is simply shading the lower edge of all the modules in the string and that's assuming that the modules are in portrait mode. So in that configuration, a little strip of shade at the bottom has the effect of reducing the current capability of all the substrings, all the cell groups, without any difference between them. So because they're all the same, the bypass diodes don't turn on and you don't get steps in the curve. So if you go all the way to the right in the block number 2 here, and you still have not found a reason for it, then there's it's possible that you have performance degradation in the short circuit current. And so you'd want to make a note to revisit this string in the future to test it and see if there's a continuing trend. Some other things you might want to check as far as your technique are shown in this gray box at the top of this horizontal row of orange boxes. In the gray boxes are measurement tips, and almost all of these groups have a group of measurement tips. So one of the things you want to check here also is to make sure that, of course, you're in the plane of the array, and does it have the same view of the sky as the strings under test? You don't want your irradiance sensor to be partly blocked by a tree, whereas the array itself is not blocked by the tree, especially under diffuse light conditions, because you may have a lot of your light may be coming from odd angles in the sky, and if you have a tree blocking the sensor's view of the sky, that's a problem, and vice versa. Is the sensor free of reflections? If you have the sensor way over to the edge of the array next to a building and a lot of light is coming from the building to the sensor, it's going to be predicting more power than you should get. And then finally, are you using the correct PV module in your performance model in the PV analyzer? Because that'll affect it too. Okay, let's suppose that we've chased that one down, or maybe we didn't even have that problem. Let's say we don't have a low ISC, so we're still chasing the reason for our low performance factor, so we drop down, take the no exit from the low ISC box, and we're next asking the question, do I have low VOC? And if so, then we, compared to, that would be number 3 here. Our curve is not going all the way out to the expected VOC. So if the answer is yes, then we enter block number 3. And our first question is to look at the VOC that we measured compared to all the others in the other strings that we've measured at that combiner box, and kind of pay attention to the spread. And if all the strings are gathered together in a tight little group of VOC values, but there are 1 or 2 strings that are 10 or 12 volts below that, or multiples of that, maybe 20 to 24 volts below, those are good. There's a good likelihood that you have a shorted bypass diode in one of those modules, taking out one cell group and causing the open circuit voltage to drop by 10 or 12 volts. If that's not the case, then and you're seeing a random distribution of open circuit voltage values, but they're quite spread, more than temperature variation across the array could account for, and especially if they're combined with other things like a more roundedness, a random change in the roundedness of the knee, then there's a good chance that you're seeing potential induced degradation, which is too deep a topic for me to go into here, but suffice to say that it is an effect in which there is actual charge migration and ionic migration within the modules themselves, which can be a permanently damaging effect. It tends to be more prevalent in strings that are biased on the negative to ground. So it showed up first in Europe, where they have bipolar or floating arrays, I should say, where half of the string is negative relative to ground. It tends to show up on that negative side, and it tends to show up more at the higher voltages, so the large negative voltages. We're starting to see this in this country. Not all is because of bipolar or floating arrays, but in negative grounded arrays too, oddly. So you really want to dial in on this early, because that's something that you definitely want to get warranty coverage for. And then, so if that's not it, then it could just be that VOC is degrading, although that's quite unlikely because VOC, in the absence of any PID effects, VOC is a very reliable, stable parameter. So continuing on down in our chase for what's causing our low performance factor, we drop down and ask the question, do we have a rounder knee than we expect? And that's a little tricky to diagnose for a couple of reasons. But we wanted to include it anyway because there is a physical correspondence to that, a degradation in the ideality factor, which is a cell parameter that has to do with how close the IV curve comes to the expected shape based on a detailed semiconductor model. The ideality factor can degrade, and that produces an IV curve like you see here, where it meets its short circuit current, open circuit voltage values, but it just is more rounded than it should be, and it misses the max power point. So that is one of the causes of a bad fill factor. That's a distortion of the curve, whereas low ISC and low VRC are not distortions. They're just compressions from left or right or vertical. Steps in the curve are distortions, and that also causes a low fill factor. Now there's another entrance to this box called rounded knee. You notice that there's another starting point for our analysis. If you already know that you don't have steps in the curve and you're not concerned about possible low ISC and low VOC, but there's some other thing that you know is affecting the shape of the curve, you can jump in here at that starting point called smooth curve but low fill factor. So if your display on the PV analyzer tells you that your fill factor is low here, but you don't see this kind of a display, you see a normal IV curve, it's just that it has a low fill factor, then you can jump into the curve right here and move on down. We've already talked about the rounded knee. The next one is to look at the case where we have a low voltage ratio. And what I mean by that, let's see, I didn't actually plan for that, discussing that, so I'm going to have to jump back to our slides. Actually, I think I have another presentation. Here it is. This is the definition of fill factor again, the area of the green rectangle divided by the area of the blue rectangle, expressing the fullness of the curve. If you have a low value for fill factor and it's a problem, what I like to do is break the fill factor into two pieces. You notice that there's the IMP divided by ISC is part of the fill factor, and VMP divided by VOC is another part of the fill factor. So it's really the product of two ratios, a current ratio and a voltage ratio. And it turns out that those two ratios represent, in an approximate sort of way, the slopes of the horizontal leg and the vertical leg of the IV curve. Mathematically, they're expressed by these dotted lines for the current ratio up at the top, the blue line, and the dotted green one for the voltage ratio. So if your fill factor is low, what I like to do is see whether the current ratio is low or whether the voltage ratio is low. Excuse me, and that gives us hints as to what's causing the issues. Let's see. I want to be back in the flow chart. So that's what I mean by low voltage ratio. It means that that your maximum power voltage is not as close to the VOC as it should be. It's shifted to the left. And so that's deviation number 5. And sure enough, you see in the IV curve here that in this measured curve, the knee of the curve is shifted way to the left of where it should be. And we can detect really small amounts of this. This is a really gross effect here. But what tends to cause that, if there's no steps in the curve and you're seeing this, this is a sign that you have excess series resistance somewhere in your string circuit, in your PV source circuit. We've never seen a case where that's caused by the connection between the alligator clip and the bus bar. It's always somewhere else. Sometimes it's a bad fuse holder. For some reason it's gotten burned and it has high resistance inside of it. Sometimes it's a somewhat burned or fatigued PV connector in the interconnection circuitries. Sometimes it's in the modules within a cell. Sometimes it's visible as a burn mark. Sometimes you can see it with your IR camera. Sometimes it's within the wiring within the module. And in this case, this is a common one where the PV module cord or conductor has become unsoldered from the ribbon within the junction box on the opposite side of the module. So with IV curve tracing, you can find this kind of thing long before it's visible and avoid losing a string because of an open circuit or having a module completely shatter because of the heat. If the voltage ratio is not low, you have a low fill factor, but that's not the answer, then you drop down one more box to check to see if the current ratio is low. And what we mean by that is that there's some slope, more slope than there should be, across the horizontal leg, in the horizontal leg of the IV curve. And you see in that first IV curve there that it's coming across a little bit too low an angle to hit that expected max power point. And this is an interesting one. This is very interesting, and if you're working in the outdoor training lab, this is a really good one to include. It turns out that if your modules are mounted in the portrait orientation and you have a sloped, a tapered dirt band at the bottom edge of the module, that will cause exactly this behavior. It's not enough difference from one cell group to another to cause a visible step in your diode, your visible steps from the turning on of your bypass diodes. It simply mushes it all together and creates this slightly increased slope. And sometimes you'll see this across your whole system. The dirt band can increase continually across the array, or it can be just repeated from module to module and have the same effect. If you clean off that dirt band, this IV curve will snap right back up to where it should be. But if you don't have that problem, if the answer to that is no, then you move to the right and check if you have possibly slightly current mismatched modules in your array. Suppose you have an array like we have at the fire station near us that has had so many failures over the years in its modules that there are 3 different types of modules that have been used in the same string. If they have a slightly different short circuit current, it's exactly the same effect as you have here. You may see a slope across the top leg of the curve with very little, if any, stepping. If that's not the case, it's possible you have degradation of the shunt resistance of the cells themselves. And what that does is it causes it is the textbook cause for increased slope in the horizontal leg of the curve. But before you decide that that is an issue, you definitely want to rule out some of these other effects. You may also see burn marks in modules which are caused by shunting effects, but those don't tend to have a widespread effect across the whole top of the IV curve of the string because they're a localized effect, and most of the modules are not affected by it. Most of the modules in the string. So that, I believe, concludes the discussion, and I have a few minutes left over for questions, so I'm going to check and see if you have any. The first one is, will this webinar be recorded and available to us after? And I will check to see if I clicked on the recording button, and if so, I will make a link available. And the next question is, what is generally a good value for fill factor or an acceptable range? And a good value is in the 90s. You want to be in the 90s. Lots of experience has shown that that is where a new array tends to be if there are no problems with shading or soiling or damaged modules. And that expecting to be within a few percent of 100 is not realistic. Either way from 100, a little bit high or a little bit below it. And the reason for that is that there are so many variables, so many opportunities for a little bit of variation to creep in. You've got the individual modules which are not perfectly matched. You've got temperature distributions across your array which are not uniform from string to string or even from module to module. You may have slightly different lighting on the modules depending upon their view of the sky. If you've got nearby shading effects that block some of the diffuse radiation, you have slight errors in your irradiance measurement. You have slight errors in the voltage and current measurements. So when you add all that up, your expectation is not to be at 100, but to be in the 90s. And third-party engineering firms are very comfortable with this. If they look at your report and they see, for instance, that your I'm going to get back to fill factor. If they see that your fill factor is nicely distributed in the range where it should be, and that your tables of values that show the translated short circuit current, open circuit voltage, and max power voltage and max power current, if they all translate to SDC at about where they should be, they're going to be really happy, and that's all inside this report. Let's see. I'll go back to the questions. I've got too many things open here. Can we get a copy of the presentation slides? I put up a PDF after each presentation. It probably won't be up until later today, and we're on California time, so you might check tomorrow. Can you discuss using the same tree over multiple measurements versus creating a new tree every time you IV trace a system? Yes, thank you for bringing that up. So I'm going to show you the PV Analyzer software here. This is how you'd be making the measurement. So when you make a measurement, you click on Measure Now, and then this is running actually a little slow because we're doing some work on it, and it's a little clunky right now. Normally, your data will come back in 4 to 5 seconds. Here's your measured curve coming back. It has a step in it, as you can see, and the curve moves over to the left, and our tree comes up. And we tell it by clicking on the string that we're measuring, we tell it where to assign and save the data. Assign means read out the module performance, the model characteristics for that particular string. Save, of course, means save the result. So since we've read out the model data, we now can create our 3 dots, and we show that, in fact, as we know from this step, we're not hitting our max power point. Because of that, our fill factor on the lower left is 0.59. Performance factor is nowhere near the 90s. So now to answer the question, you'll notice that if I click on Recall and go back to this tree, in the tree it tells us that we have 2 measurements in inverter number 1, also 2 measurements in combiner number 1. And those 2 measurements are 1 measurement each for string 1 and string 2. Now, in fact, we can make as many measurements of string 1 as we want over as many years as we want, and all it's going to do is it's going to add the number of measurements in this measurement record over on the right-hand side. That select measurement list is where we select which measurement we want to recall for viewing. And every measurement is time and date stamped, and it's also stamped with the location in the system. So if there's any question later on, it's very definite. So what this means is that in response to the question, when this data is at some future date, this data can be exported and explored for trends. We can go, for instance, to string number 1, which might have 5 measurements taken over 5 years, and we can recall and look at the trends. And that reminds me of another thing I wanted to show you today, which is that we are in the development stages of a new data analysis add-on feature for the PV Analyzer, which will be sold separately at a reasonable cost. And it will bring some very powerful data analysis tools into the PV Analyzer software itself, so you can use them in the field or in your office. And I just put in one example of that. So you'll see that there's an analysis tab in the software, and this is an example of what we could do. We could show a whole combiner box worth of IV curves in one plot. This would be useful when you're finished with a combiner, when you're commissioning, or you're doing a recommissioning because you're taking ownership of a system. You can measure your strings at the combiner, and then you can look at them and see how tightly they're bunched. Or you could display a histogram of fill factor for the whole system or for a given combiner box. And you can also do things, I didn't bother to put this into the mock-up yet, but I'll show you the another example of what we could do, which would be to have an interface like this, where you would, in that analysis screen, you would migrate to a certain spot, like to a string, and select a range of dates, and ask it to plot the performance factor and the fill factor as trend lines over that range of dates. So what we're doing here is, like I was saying a minute ago, we're basically mining our historical data for that particular string and showing the trends. And we expect to be able to do that at a higher level as well, to be able to, say, click on the combiner or the inverter and plot the average, the trends for the average performance factor and the average fill factor for that whatever level you select in the tree. And that'll be very powerful especially for people who are doing O&M work, because this is their bread and butter. I mean, you can get bonuses if you can keep the performance high on a system over the years, and this tells you exactly what's going on. So I'm going to check and see if there are any other questions. Here's one. When you extract data to create reports in the Excel workbook, can you simply select which year to export? No, unfortunately, that's going to have to wait until this data analysis add-on is developed. The PV Analyzer software only exports the most recent measurement for each string. And another question, do you set up the tree ahead of time or while you're at the site? What I do usually, if I'm going on like a demo trip or I'm going out to help troubleshoot an array that's having trouble, some customers having trouble with it, I will usually ask them for a one-line diagram ahead of time, and I will create a new project before I go out. And I'm going over time here, but for those of you who may be interested, you might want to just stick around for this. If you have to leave, thank you for participating, and please let me know if you have any further questions. Just drop an email anytime. So if you were setting up your project, you would go to New Project, and you fill out where the system is. If it's on a rooftop, and you can use the rooftop to figure out what your latitude and longitude is, you can click on the roof measurement tool, and it'll take you to our website, and that's cool because it'll fill in latitude and longitude for you, and it'll also tell you what the orientation of your rooftop is. If you're not on a building, or you're not going to have your array parallel with the roof, you can just ignore that part of it, but you can still use the roof measurement tool to get your latitude and longitude. You want to make sure your project time zone is set properly, because we actually calculate where the sun is at every moment that you take your measurement to optimize our model. So once those things are all filled in, you go here, and I'm going to answer your question about the tree in just a second. You pick your module maker and your model number from these drop-down lists. I'm just going to randomly pick some. And then I create my tree. And this is where it's helpful to know how the system is designed, what its what its configuration is. So in a lot of cases, in large systems, you have many inverters with identical array designs. And in that case, I use this autofill tree icon. And I'll tell it how many inverters I have, whether I've got combiners, how many combiners for each inverter, how many strings per each combiner, and how many modules per string. And then click OK, and it creates the tree. And you don't see everything right away because that would be it would require a lot of scrolling to get to a place. So we just collapse the tree initially, and you click on these small arrows to expand to whatever level you want to work at. So I do that ahead of time usually just because it's more comfortable in my office than it is either in the front seat of my truck or on a rooftop, and the lighting is better, etc. Plus, you don't want to waste valuable time in the field doing office work. So I'm going to check and see if any other questions have popped up in the meantime. I don't see any further questions. Let's see, I'm going to drop back to the, so we still have quite a few people online, so I'm going to switch to another set of slides and see if you're interested in this. I think from a professional standpoint and a business standpoint, it's really important. I recently gave this presentation at the Sandia EPRI O&M conference in Palo Alto, and I'd like to touch on just one project that I discussed in that presentation, which is the development of a guide to performance and safety measurements for commercial PV system commissioning, which is being done under the SunSpec Alliance and is a multi-year project that is coming to a close hopefully before Solar Power International this fall. And it's based on the concept illustrated in this flowchart here, which is that starting at the bottom, if we improve our commissioning measurement practices, we'll have earlier exposure of performance issues and earlier resolution. And therefore, we'll have our performance assessments made in the early life of the system will be more detailed and more reliable. That will also provide feedback into our design and construction practices. For instance, maybe we learned that our modules were not being mounted in a consistent orientation, or maybe the ventilation was poor underneath the modules, or maybe I forgot the third one I was going to mention. But anyway, we can improve our design and construction practices, and then we can verify that next time we design a system. We do the commissioning measurements and we verify that, yeah, we've done that. But maybe we discover some other issues. So this can be a virtuous loop or a virtuous circle, as they say. It's a really important system diagram that it has to do with continually improving things. And some of the offshoots of this are, up on the upper left, reduced O&M burden and improved return on investment. And on the lower right, eventually a reduced risk and cost of capital and lower cost of energy. So these are all things that are important business objectives for any business, and they can all come from more detailed and more reliable commissioning practices. So what we're doing is developing this guide with the goal of reducing the cost of energy for commercial scale systems by advancing best measurement practices in commissioning. And we're going to have chapters on an introductory chapter that establishes the business case, and then chapters on system AC performance, which is measurement of energy and instantaneous power compared to predictions. This is a really important topic that very few people understand, and we're going to make it clear. We're also going to talk about array performance measurements, which is the type of thing that we've been discussing today. We'll have a chapter on insulation resistance measurements, one on infrared measurements, and one on solar access or shade measurements. And I think that's all I wanted to mention about this project, but I'd like to close just by mentioning that it's an industry collaborative project, and we now have the infrared measurement chapter available for review. So if your organization would be willing to review that chapter and send us either a marked up version of it using track mode in Microsoft Word, or just send us your inputs by email, we'd love to have that, and it all adds. And any organization that contributes to that will be listed as one of the collaborators and one of the helping organizations in the guide itself. As time goes on, we'll have these other, the next few months we'll have these other chapters available as well for review. So please let me know if you'd like to, specifically whether you'd like to review one of these chapters or whether you'd like to review them all. So I'm going to go back to the questions block and see if there are any further questions. Okay, well, thank you very much for participating today, and I wish you all the best in the solar field. Please let us know if you have further questions. If you're a PV Analyzer user already, which I know a number of you are, let us know how you're doing. If you're not, let us know if you what we could do to help you make you a PV Analyzer user. Thanks much. Goodbye.